you unmute, please?
Okay, fantastic.
So when I get into this, I will mute everybody. There you go. And Ben, you unmute.
Perfect. So you can hear me loud and clear?
Yes, if I haven't muted myself. Yeah, that's good. Yeah, good.
Perfect. So thanks very much, Paul. And thanks very much to Terry for inviting me to speak as well. So I suppose, like you said, I'm Ben, and I'm a first-year PhD student here at NUI Galway as part of the Applied Optics group, and I am currently studying adaptive optics. So I thought this would be a nice topic that would dovetail quite nicely with an internship I was lucky enough to do last summer with Dr. McKeon, who was a member of faculty here, and he had a considerable interest in SETI. So he was the one who introduced me to all of this. So I suppose without further ado, we'll kick off. And whenever I'm talking about these kind of subjects, I always like to include this quote here by Arthur C. Clarke. And obviously, I suppose, if you think about it rationally, there can only be two possibilities, that either we are alone in this universe or we are not. But again, he's certainly not wrong that it is equally terrifying either which way that question comes to be answered. And I suppose to further consider the question, you might wonder why we do it at all. Are we just looking for a good scare? But I suppose obviously not. In reality, I suppose the main motivator here is to learn a little bit more about the universe and develop all of the technology that goes with that. So again, moving on. So again, there are two topics that I'm going to be covering primarily. So the first one is SETI, which is the search for extraterrestrial intelligence, and whether or not we have company in this universe of ours, followed then by a little bit of my current research, which is on adaptive optics. So I'll explain a little bit more about that in a little while. So starting with SETI. So first of all, what is it? Like I said, it's the search for extraterrestrial intelligence, which is often described as the act of searching for technosignatures for advanced alien life in the cosmos. The term technosignature is often compared with the term biosignature, which is used by, I suppose, exobiologists and anybody who'd be interested in alien life that way, to describe signs of life elsewhere in the solar system and indeed the galaxy at large. However, what sets SETI apart is that we're looking for intelligent life. So we want some kind of evidence that whatever life that may be out there somewhere would have the capability of using and developing technology that would allow them to communicate with us. So some of these technosignatures would include, I suppose, any evidence of these aliens being able to communicate with each other and across interstellar distances to, I suppose, extend that to a more advanced scenario. But there's also some more simple evidence that could be available, such as light pollution, for instance. I suppose alien cities, alien settlements, all of that kind of stuff. And to date, most of the work in terms of SETI is done by the Berkeley SETI Research Center and the SETI Institute, which are both based in California. And then I suppose just addressing this picture here, this is a Dyson sphere, which would be a very extreme example of a technosignature of a much more advanced alien civilization than us. So what a Dyson sphere does is it is a contraption that is able to harvest energy from a nearby star. Again, we are nowhere near developing this kind of technology, but it's usually a nice kind of yardstick for thinking, okay, so if we can discover something of this magnitude, surely we know what kind of alien civilizations we might be dealing with. Unfortunately, we don't think we have seen any of them yet, but that doesn't mean that there hasn't been anything interesting in the meantime. So just to bring it back to where it all began, it was first suggested by McKeon and Morrison when they wrote a paper, and they thought that maybe radio could be used as a means of contacting extraterrestrial civilizations. They thought that radio was ideal for communicating across the vast distances of interstellar space. So that obviously inspired Frank Drake, who is there in the picture on the left, to kickstart what was called Project Ozma, named after the Queen of the Land of Oz in the Wizard of Oz books. And what he did is he used the radio telescope that we see behind him, which was a precursor to one of the radio telescopes that is currently used today to search for extraterrestrials. So what he decided to do was he observed 2 nearby sun-like planets at a frequency of 1420 megahertz, which for anyone who has a little bit of physics experience, this is the frequency at which the electron in a hydrogen atom will change from a spin up to a spin down state. Again, don't worry if that doesn't register with anyone, because I suppose it's just a bit of trivia, really. It's I suppose just what Frank Drake decided to do. He thought that this would be a frequency that would be universally known among any extraterrestrial who had the capability of using a radio. And I suppose to bring things back to Earth, it attracted the attention of the Soviet Union. And again, this was the height of the Cold War. So again, America and Russia were at loggerheads. So if America were doing it, surely the Soviet Union wanted to be the ones to detect aliens first. So they did their own research on SETI and tried targeting a few different stars, but they didn't seem to have any more luck, unfortunately. Then moving on to between the 70s and the 90s, there were a number of American observation programs, particularly Project Cyclops, which was actually funded by NASA. So it's interesting to note that NASA even had a hand in this whole endeavor. But I suppose as well, it wasn't just big government agencies that had a unique kind of interest in this. There was also the Planetary Society, which had Meta and Beta. I'm a member of the Planetary Society, I might add. They're fantastic, actually. And then Serendip, which was run by the University of California. So then finally, unfortunately, in 1992, NASA withdrew their funding. So ever since, it has been primarily been funded by private investors. Which brings us to Breakthrough Listen, which was announced in 2015 by billionaire Yuri Milner. He listed a bunch of different initiatives that he wished to fund. And there was a big lavish launch party. I think Stephen Hawking was invited. So anyway, Breakthrough Listen is the one that he decided would focus on looking for extraterrestrials within our galaxy and even further afield. So what he did was he allotted $100 million to survey 1 million nearby stars and the centers of 100 nearby galaxies, which would take, I suppose the best guess, about 10 years. So Breakthrough Listen has access to the Green Bank telescope, which we see here in the picture on the left, 20% of the time that it is operational. And then the Parkes radio telescope in Australia, they have access to that 25% of the time that it is operational. I've had the pleasure of using the Parkes telescope, actually, and there's ongoing SETI work that happens regularly there. So if we find anything interesting, I'll be sure to let you all know. However, these aren't the only radio telescopes that Breakthrough Listen have access to. Meerkat in South Africa and I-LOFAR in Europe are also used by the Breakthrough Listen project. And interestingly, there is an Irish stake in this, obviously, because we have our own I-LOFAR station in Birr, County Offaly. So delving into a little bit of that. So how we use I-LOFAR to search for aliens is NASA have a mission called the Transiting Exoplanet Survey Satellite, which is just called TESS for short. And what that did is it conducted an all-sky survey and surveyed 200,000 stars, searching for exoplanets around these stars. So all of these stars that were surveyed, any of them that were found to have exoplanets, were put into a list. And then within this list, what we did is we decided which of these stars were visible simultaneously from Birr in Ireland and I-LOFAR SE, which is located in Onsala in Sweden. So these stars were then observed for 15 minutes at the same time using both stations. And to date, we have managed to observe 38 stars successfully. It was a little bit slow to get going, unfortunately, because, again, there was just software issues and even a little bit of trouble with hardware and all of that kind of stuff. All of the usual kind of technical glitches that one might expect when using this kind of technology. So we were hoping to survey a few more last summer, but unfortunately we only managed 38 out of a list of a couple hundred, but I'm sure we'll get there eventually. However, we haven't managed to intercept any extraterrestrial transmissions yet. So I don't want to be too fatalistic there and say, no aliens yet. So Again, even though we haven't discovered anything in Ireland, how many civilizations, for instance, could we expect to come into contact with? So this equation here is the Drake equation, and it was formulated by Frank Drake, who we saw a few slides ago. So he decided to try and put a number on how many different alien civilizations out there we could potentially contact. So he invented this equation, which is a number of terms here, and each of these represents a different factor that he thought would be significant in guessing how many of these aliens, alien civilizations even, would be, I suppose, within range of us contacting. So first off, or star, describes the average rate of star formation in the Milky Way. Best guesses at the moment look at about 1 star a year. So there is about 1 new star every year forming in the Milky Way. And then the next number, FP, is a fraction. So again, this would be a number between 0 and 1. So it would be how many of these stars would have planets. So if we multiply this number by that, we basically get the number of planets that form and the fraction of those that have planets. And then further to that, we get NE, which is another fraction, and it represents the number of these planets that could potentially support life. But the thing is, just because planets could support life doesn't necessarily mean they do. So that's why we have the next term here. So this represents the fraction of those planets which could potentially develop life, and then those of them that actually do. But furthermore, developing life is all well and good, but how much of that life is potentially intelligent? So then we have the next term to describe that scenario. And then moving further on, we have the fraction of civilizations that have the technology to send signals into space. So while the life might be intelligent, are they intelligent enough to develop, say, radios or the technology to be able to communicate across the vast distances of space? And then this final term here is L, which describes the length of time that these civilizations have been sending signals into space. So once we crunch the numbers, one might ask, so do they all add up? Again, we have no idea of what the exact value for any of these are. So in most cases, we have to guess. And even further to that, there's only one advanced civilization that we know of that we can use as a template, and that's us. So again, using all of these various assumptions, there's been many prominent guesses, and Carl Sagan was very optimistic. He assumed there'd be about 1 million different alien civilizations out there in the Milky Way that we would be able to contact. There are others that aren't so hopeful. So worst case scenarios even give the number at about 100, which when you think about it isn't awful, because I suppose if you were to be completely doom and gloom, you'd probably assume that there's absolutely no one out there. So even being realistic, and while also being, I suppose, to a certain degree pessimistic, there are even some alien civilizations out there that we could indeed contact. And I suppose another interesting topic to deal with is this Drake equation concerns planets, but what about moons? Because there's been much talk, particularly in the last decade or so, of the potential of there being life on some of Jupiter's moons, namely Europa, which has a subsurface ocean. There could be life on that moon, even though it might not necessarily be intelligent, but it is a point you can raise. Also, I just thought I'd include this image here of Frank Drake's number plate. So he's quite optimistic. So what Frank Drake believes is that the equation on the previous slide could be quite significantly simplified, because this number here describing the rate of star formation works out at about 1 star per year at our best estimates. And because these numbers here are all fractions, he assumes best case scenario, because this is 1, and then assuming that the maximum probability here for these fractions, these numbers would all be 1. So we have 1 times 1 times 1 times 1 times 1 times 1. So that's all 1. And then, like in his number plate, we just get left with n is equal to L. So Frank Drake is very much an optimist. He definitely believes that there are at least some aliens out there. So even if we are as optimistic as Frank Drake, have we had any hope of contacting them yet? And we have certainly had some interesting signals. So first off, we have the WOW signal, which is fairly famous. It was detected back in 1977 by Ohio University using their Big Ear radio telescope. And the signal came from the constellation Sagittarius. The telescope was a fixed telescope. So unlike the Parkes radio telescope that we saw, or the Parkes and the Green Bank telescope even, that we saw a few slides ago, that can move, the Big Ear was fixed. So it could only observe stars for 72 seconds at a time. However, this signal lasted for the entire 72-second duration that the telescope could observe the signal for. Again, the signal was transmitted at 1420 megahertz, which was the same frequency that Frank Drake used when he was listening in for alien transmissions. What makes it even more interesting is this frequency is forbidden for all Earth-based signals. So it is actually illegal to transmit at this frequency because it is reserved for radio astronomy. Unfortunately, the signal has not been detected since. And so to explain this picture slightly, so we see a printout of different numbers and letters here. So these would all describe how high above the noise baseline the signal was. So what we see here are, within the numbers anyway, I suppose anything less than 10 times above the baseline was assigned a number 1 to 9. And then after that, in intervals of 2, each letter was then assigned to how many times above the baseline it was. So for 12 times above the baseline, it might be A. For 14 times above the baseline, it would be B, and so on. So they got as far as Q and U, which worked out at about more than 30 times greater than the noise baseline that the telescope was detecting. So it was definitely a cause for someone to exclaim, wow, which is how the signal got its name. However, even though we haven't observed the signal again, it still is the best candidate for a call from ET because it bears all of the hallmarks of a signal that we would send if we were to want to make ourselves known to aliens out in the cosmos. Even still, though, this was not the only signal that has been detected. We look like we might have had another missed call recently. So in April and May 2019, the Parkes telescope in Australia detected an interesting signal from Proxima Centauri. The signal was detected using Turbo SETI, which is software that I had the pleasure of using last summer during my internship. And again, this is designed to separate potential signals from noise based on different parameters that are given. So if you want to look for signals with a certain signal to noise ratio and all of these other different parameters that you might use. So this signal in particular became known as BLC1, or Breakthrough Listen Candidate 1, and it received a significant amount of media attention. A lot of popular media sites covered it, and they were all speculating, have we finally heard from aliens out in the cosmos? Unfortunately, like the WOW signal, trying to detect the signal again was a failure. No one has managed to detect it since. And however, unlike the WOW signal, which we're not quite sure how it was, I suppose, generated, this seemed to be caused by human radio interference. So just to give a flavor of what radio astronomy has to contend with, if we look at all of these bright yellow little boxes scattered throughout the diagram, those are particular frequencies, at least in the US anyway. There isn't quite the same level of cohesion within Europe. It varies from country to country. So it's very difficult to get an idea of what different frequencies are reserved for different uses and so on and so forth. However, in America, again, all of these yellow boxes are reserved for radio astronomy, but we see that there are lots of other uses that take up vast swathes of the radio spectrum. And unfortunately, you see, the thing is, even though this frequency is blocked off here and here, say, it might creep over into other bands. So just because a certain use is assigned a different frequency doesn't mean that it necessarily stays there. So there's a lot of kind of crossover between different frequencies. So unfortunately, that means that radio astronomy has an awful lot to contend with. And it is quite literally like searching for a needle in a haystack, which is a term that's used quite often by the SETI community. They talk about searching through 8-dimensional haystacks. to try and find evidence of extraterrestrial life. So obviously there's a lot of barriers to effectively carrying out a radio SETI search. Obviously, like I said, radio frequency interference makes this quite difficult because there are simply so many electronic devices there that could completely throw us off. Even phones, local radio, cars, air traffic, and I know they're not quite as popular here, but certainly in America, even garage door openers, the gadgets that people would use to control the garage doors, they emit radio waves, which could even throw off a very sensitive radio telescope. One particular solution involves using a bandpass filter. So this would create a block for certain frequencies and would allow us to focus on a certain portion of the radio spectrum. But it's not a perfect solution. And even further to that, we don't even know what frequencies are the correct ones to allow, because we just don't know what frequency we might have to listen to if we wanted to tune into Alien FM, should we say. Unfortunately, there is another growing problem that is becoming more and more of a concern of late, and that is the emergence of satellite constellations, such as Starlink and OneWeb. They're becoming a significant challenge as these are downlinking significant amounts of data to Earth. They interfere with radio SETI in particular, but unfortunately, there's other branches of astronomy that are also falling victim to the problem of large satellite constellations. So with that in mind, using optical telescopes, which are telescopes that use visible light, using them for SETI searches is becoming much more popular, simply because they aren't affected by radio interference, but unfortunately they are quite a bit more expensive to build. So here on the left, for instance, I have an example of Lake Observatory's automated planet finder, which is also located in California. It's not far from where the SETI Institute do much of their work. This is the optical telescope that they would use to search for any evidence of aliens. In particular, they would search for exoplanets, which might be emitting light pollution, laser pulses like beacons or whatever, almost like a lighthouse trying to be found in the vastness of space. Or even, like I said, in one of the earlier slides, some outrageous technology such as a Dyson sphere even. However, optical telescopes aren't perfect either. They're affected by the weather. Again, if it's raining, for instance, or even if it's cloudy, they're no good. And unfortunately, they're not immune to the effects of Starlink either, as bright streaks have often appeared in optical images taken by large telescopes around the world. So addressing the problems that optical telescopes might face, that is where adaptive optics comes in, and that is what I'm currently researching. So just to start off, what are adaptive optics? First and foremost, they are used primarily to compensate for the effects of atmospheric turbulence, because unfortunately, like say the Hubble Space Telescope or the James Webb, putting a telescope in space means that you don't have to observe whatever target star you're looking at through the atmosphere, which has the effect of negatively influencing the light. It would aberrate the images and I suppose cause other unwanted effects, particularly for telescopes that have large primary mirrors, particularly greater than 4 meters. Adaptive optics considerably enhances these telescopes' imaging capability, because these telescopes would have the capability to collect an awful lot of light. And obviously, if you're collecting a lot of light and that is affected by the atmosphere, even though you're using a large telescope, the image quality could still be considerably less than what you might expect for using such a massive mirror. And adaptive optics has kind of become a household name in the astronomy world. So they're used as standard on most of the world's operational large telescopes, like for instance, the Keck telescopes here and the Subaru telescope, which are all situated in Hawaii. And just to draw your attention here, we have what look like laser beams coming out from the telescopes. So in these two coming from the Keck telescope and here also with the Subaru telescope, these are what are known as laser guide stars, and I'll explain a little bit more about them in a few slides' time. So obviously, why would we use it? Like I said, light does get bent by the atmosphere as it passes through space. I like to include Pink Floyd's Dark Side of the Moon here because it illustrates the effect quite nicely. So what we have is obviously the starlight coming in from space. And then if we think of the effect of the atmosphere, a bit like a prism, it spreads it out, and obviously it negatively affects any images that we might want to take. So the only thing is, though, unlike this prism, which bends the light by a constant amount that we could always compensate for, the atmosphere is constantly changing, and the amount of, I suppose, the amount of bending that occurs isn't constant either, because that depends on the temperature of the atmosphere, the humidity, altitude, and a range of other factors that cause it to change on quite a rapid time scale. So usually this effect is quite small. I want to emphasize, so it's not drastic as, say, what happens when you put a pencil into a glass of water. But unfortunately, like I said, for telescopes that have large primary mirrors, the image quality is reduced quite a bit. So again, here we can see why we need adaptive optics. So we have images here of Saturn and Uranus, both taken in the infrared. And then obviously without an adaptive optics system being used, we see that the images are quite blurry. So once the adaptive optics system is switched on, we can see some of Saturn's moons. And also here on Uranus, we can see different bands, and we see this band here close to the poles. So what happens with the atmosphere is, if we see the light waves traveling through space, and then once they reach the atmosphere, I think a nice way to think about it is if you think of the atmosphere as like a patchwork quilt of air over the telescope. And this R0 number here describes the size of the different patches in that quilt. So you're going to get alternating patches of air where there'd be negligible turbulence, so where the light isn't affected much at all, really. And then there'd be other areas where the starlight is bent quite a bit. So after the light passes through the atmosphere, we get something quite like this. So rather than everything being nice and flat, like it would be if it was just coming through the vacuum of space, what we get here is we see that the light waves get bent quite a bit. And obviously, because these light waves don't hit the detector all at the same time, so this bit here will be hitting the detector in the camera a little bit before here, we see that things get a bit shifted, and obviously we want to be able to correct for this. So the main point of adaptive optics allows us to use mirrors that are able to change their shape and correct for this effect. So in general, the different system components that are used as part of an adaptive optics system, like I said, the deformable mirror that would allow us to compensate for that effect. It's able to change its shape to match the incoming light waves. There's different ways of creating mirrors that are able to do this. One common way is if we're able to get a mirror that's a little bit bendy, if you think like it's a bit floppy like a sheet of plywood, and if we stick it on a set of supports, and then we're able to manipulate that mirror because there's a bit of give in it, and able to get it to change shape to however we would like it to in order to compensate for the effects of the atmosphere. Like I said a few slides ago as well, the laser guide stars that were being shot from the Keck and Subaru telescopes, they're used to sample the atmospheric turbulence, because what used to be done is natural guide stars were used. They were common in the early days of adaptive optics. So what this would involve is if you had a star that you wanted to observe, in order to be able to sample the atmosphere, you needed another bright star near it in order to gauge how badly starlight was being affected by the atmosphere. However, this severely limited the use of adaptive optics because it only allowed astronomers to use it to observe stars that had a bright star within a relatively short distance from the target star. However, because we can use laser guide stars, it allows us to use it over the whole sky, because it allows us to generate a guide star wherever it needs to be. And this is quite useful because what it usually involves is shooting a sodium laser, as we saw with the telescopes a few slides ago. And what that does is that interacts with a layer of sodium ions that are present in the upper atmosphere. And based on the level of interaction with those ions and then the laser beam that is being shot at them, we can gauge how badly the atmosphere is affecting the starlight. So it's all well and good to be able to see that the atmosphere is affecting our images using the laser guide stars, but then obviously we need to be able to quantify and measure this effect. So that's where a wavefront sensor comes in. It measures the difference between the refracted light waves and then what scenario would be there if light was not refracted at all. So as in if the light was coming straight through from space and as if Earth had no atmosphere. There are different types of sensor available. I focus on one particular type of sensor that I'm going to describe a little bit in detail in the next slide or two. Obviously, we need a way to change the shape of the deformable mirror. So that's where actuators come in. So like I said, with a floppy mirror, you put a bunch of actuators behind it, and these are little mechanical devices that they'll poke and prod the mirror just to be able to change its shape in order to get things the way we want it. And then finally, we need a control algorithm. So what this does is it takes the data from the wavefront sensor, and then it converts all of that data into useful commands for the actuators. So for instance, that you would be able to say that, oh, well, if the atmosphere is affecting our images this much, that we will be able to correct for it to this degree, and so on and so forth. So it's like coding. So it is basically able to say, if the atmosphere is doing this, we do this. And I suppose just moving on then, the two areas of my research that have dealt with adaptive optics components so far are primarily the wavefront sensor and to develop control algorithms to reconstruct the incoming light waves as they approach the telescope. So first off, with the wavefront sensor, the one that I have looked at the most is called a pyramid wavefront sensor, and it is the most sensitive sensor available for adaptive optics. However, the primary element of this sensor is a glass pyramid, and while it is the most sensitive, it is usually the most difficult and expensive to manufacture as a result of having to manufacture this glass pyramid here to the correct specifications, particularly machining the tip to such a fine point that we get the images that we would like. Pyramid wavefront sensors, because of their sensitivity, are often employed in extreme adaptive optics systems. For instance, the Subaru Extreme Adaptive Optics System uses pyramid wavefront sensors, and that's obviously located on the Subaru telescope that we saw a few slides ago in the image. So what happens here is when the incoming light reaches the telescope opening or aperture, that is then focused onto the tip of the pyramid, and then this spreads the light out into 4 different images. So it allows us to look at the light through 4 different lenses, should we say. So again, these solid lines here are what would happen if the light coming in was perfectly flat, and it would just be mapped onto our detector plane as if there was no atmosphere there at all. And that's what we would love. But obviously, with the effects of the atmosphere in the way, that isn't the case. So what we see here is a different wave that has been modified by the effects of the atmosphere. And then once that is focused onto the tip of the pyramid, we see that it instead follows these dashed lines. And we see that the image is slightly offset from where it would be in the ideal scenario. So what that allows us to do is it allows us to measure the difference between these two scenarios. And based on that, we're able to gauge how badly the atmosphere is affecting our images. However, one small catch is that the pyramid wavefront sensor is usually only useful when all of the light is focused to a small region within the tip of the pyramid. So in order to make it useful over wider ranges, what you can do is you can hook the pyramid up to a system that allows it to move. So we could move the pyramid in a circle or from side to side. So that would allow light to spend more time in each one of the 4 quadrants of the pyramid, so that each of these 4 images might appear a little bit brighter, and we'd be able to look at each of them in more detail. So that's called modulating the pyramid. And like I said, it's a way of increasing its useful range. It's very, very useful. And it is employed on most adaptive optic systems that I know of. So then it's all well and good that we have this data. So how do we then use it in order to accurately reconstruct the incoming light waves? So obviously we need different mathematical formulae in order to do this as a way of describing the turbulence introduced by the atmosphere. And one common choice, these are called Zernike polynomials, and they were developed by a Dutch physicist called Fritz Zernike. They were originally introduced for microscopy, and they have since been transferred to astronomy. They're often used for telescopes that have circular openings or apertures. And what's nice about that is that these have a nice mathematical property that allows us to decompose any turbulence that is introduced by the atmosphere into any of these. So we can almost think of the atmosphere as almost like a soup. So the different negative effects that it introduced might be a little bit of this, a bit of that, some more of this, maybe a small bit of that, not so much of this. And then I suppose all of the different combinations that there might be. However, that these will only work for a telescope with a circular aperture. We'll have to use different formulae if the telescope opening is a different shape. So say, for instance, if it was square or if it was annular, which is basically it is circular, but then there might be a small obstruction in the middle for maybe your secondary mirror or something like that. You're going to have to use different formulae then. So while these are commonly used, there are other formulae that are also used for different telescopes that have different opening shapes. So then obviously the goal of that is to use this data, which has been processed by the algorithm, to control the deformable mirror to filter out the adverse effects of the atmosphere, to hopefully image exoplanets. So what adaptive optics allows us to do here is normally these stars here, this one is 21 or 2M1207 and TYC8998 761 are these two stars here. And normally these would appear far too bright that they would drown out the light of the planet here and these planets here and here. However, once we introduce an adaptive optics system, it can filter things quite nicely, and it allows us to also see the light from the different planets rather than just the star, and it allows us to take images of them. Again, it's still early days in the grand scheme of things, such that we only know that a planet is there. We can't image it in much detail. We can't really see anything other than a blob of light, really. So hopefully in the future, what we might be able to do is to develop on that. And for instance, the extremely large telescope, which is being built by the European Southern Observatory in Chile, is going to have an adaptive optics system implemented into it. And this is called MAURI, which stands for Multi-Conjugate Adaptive Optics Relay. And that is something that I'm hopefully going to work on over the next couple of years. However, another interesting technique that is often employed is using artificial intelligence as a control algorithm, which allows to deal with atmospheric turbulence in a more general sense, whereas more traditional algorithms would probably be a bit rigid, shall we say, in their ability to deal with the effects of the atmosphere, where it is usually a case of, okay, if the atmosphere is this bad, we do this. So that even if there's a slight deviation there, it might not be able to compensate for it as much. However, artificial intelligence could deal in more general scenarios. So it might be able to generalize for the different effects of the atmosphere a little bit better than might be the case if we used a more traditional algorithm. Further to that even, we might be able to develop adaptive optic systems where there are no wavefront sensors at all, which would be useful in the sense that it means that we wouldn't have to manufacture expensive glass pyramids or anything like that. We could develop computers and software to a point such that all of the correction is done in post-processing, and there's no need to do it using hardware like the glass pyramid, for instance. Another interesting, again, it's almost quite literally pie in the sky, the solar gravitational lens, which is the plan to use the sun and Einstein's theory of relativity to use the fact that the sun and its gravity has the ability to bend light, and to employ that and use it as a very powerful lens would be a very interesting technique in hopefully imaging the surfaces of exoplanets. But obviously, because this is such a massive project, it's going to require adaptive optics, particularly if we want to observe exoplanets and I suppose the continents that would be present on those. We're going to have to look through the atmosphere. So again, adaptive optics is going to be instrumental if we want to eventually carry this out. And then finally, hopefully to increase the resolution of exoplanets, like I said, in greater detail, so that we could hopefully observe alien megastructures, settlements, even pollution. pollution is usually a good indicator of alien life. So again, if we're able to see light pollution in particular, we know that there's technologically advanced aliens that have the capacity, at the very least, to even generate electricity, maybe. So again, these are all updates and advances that might be a bit off. So what can we do in the meantime? So taking it back a little bit to radio SETI, it's not redundant just yet, at the very least. Obviously, again, optical is usually a bit more robust to the effects of radio interference, but that doesn't mean that radio SETI is useless. It's still a very valuable tool for conducting SETI searches, and a great deal of SETI is still carried out in the radio regime. However, unfortunately, it is still quite lacking in the optical regime in terms of support. So SETI proposals rarely get much time on the world's most powerful optical telescopes. So for instance, if you wanted to go to the Subaru telescope or the Keck telescopes, or even the extremely large telescope in Chile in due time, and say that you wanted to conduct a proposal to search for extraterrestrial life, unfortunately, they probably wouldn't take you seriously. And they would probably favor other proposals that might say, I don't know, look for evidence of dark matter or gravitational waves or anything like that. So sadly, SETI doesn't get much support. So that's why to be able to advocate for it and to support it is very important. So with that in mind, what you could do if you're interested is join a group like the Planetary Society, of which I'm a member, to show support for a SETI campaign. And even still, if there are no aliens, that's no problem, because there's probably plenty of new physics to be discovered. For instance, I think a great example of this is Jocelyn Bell, who discovered pulsars when she first observed the signal coming in on the Jodrell Bank radio telescope in the UK. The pulse was very regular, and she thought this couldn't be natural. She thought it had to be artificial. So she nicknamed the signal LGM, which stood for Little Green Men. However, on closer inspection, it showed that it wasn't little green men sending the signal at all. It was actually a pulsar. It was a star that was pulsing very regularly and sending out radio waves that could be measured with a detectable interval between them, so that even though this looked at first glance like something that was very artificial, it was actually something natural. And I suppose that's the great thing about this, that even though the end goal of SETI is to search for extraterrestrial life, there's also lots of other interesting stuff that falls out along the way. So yeah, that's pretty much all I have. So thanks very much for listening. And if anyone has any questions, I'd be happy to take them. I see that there's a few questions here in the chat.
So and that's brilliant. Thank you. Most illuminating presentation, and really, very interesting and amazing how far we've come, isn't it? But I'll just have one little question myself, because that's my privilege. I get in first. But how close? I mean, you talk a lot about adaptive optics as being the standard tool of preference. Here we've now got not just the Hubble, but we've now got James Webb being collimated, for want of a better word, and it's in position and so on. How close are ground-based adaptive optics versus space telescopes now?
In fact, actually, well, I think there was a recent paper I read about the extremely large telescope in Chile, and once that is built, that's going to have better resolution than even James Webb or Hubble. So the thing is, there is definitely still an advantage to building ground-based telescopes, because it allows us to build larger telescopes. Again, the main limiting factor at building large space telescopes is the cost and the difficulty of putting them up there. So, I mean, while ultimately it would be lovely to build something the size of the extremely large telescope in space, again, there's just different logistical constraints that just mean it's impractical. But that said, it isn't all doom and gloom, and it's not awful in the sense that we are still able, with adaptive optics technology, able to develop ground-based telescopes that would have better resolution than Hubble or even James Webb, because we are able to develop the technology on the ground even though to implement it in space might be a bit more burdensome.
Okay, that's good. Shall we go and have a look at the chat and see what we've...
Absolutely. I saw, I think Terry asked 2 questions there. He said...
Terry's got a couple of questions in. Go on, Terry.
Right, well, you can read them. First of all, thanks. A brilliant presentation. I learned quite a lot of new stuff there about adaptive optics.
My pleasure.
I'm just wondering, first of all, in terms of RFI, with the move towards autonomous self-driving vehicles, are they going to create a lot more interference, or is the frequency not one that will interfere?
Well, you see, the problem with RFI and autonomous vehicles is they'll need to have some form of onboard radar in order to be able to sense the road in front of them. So the problem there is I'm not entirely sure what frequency that's at, but if it's similar enough to air traffic, I'd say radio SETI could be in with another problem to have to contend with if someone is driving, or well, I suppose even a car more particularly is driving itself close to a radio telescope. We could have another issue to deal with there, in the sense that, again, if this car is using its radar to be able to drive itself, that could be generating interference for the radio telescope. Yeah.
Thanks. And the other one then was about the lasers. I thought that they all used an orange laser, which is basically the sodium color. But I saw that the ones that you showed of the Keck were 2 green lasers. So is there a difference, and what are the advantages?
Actually, that's an interesting point. You see, what happened there was, I think it's just the color correction in the photo, because ultimately sodium laser guide stars tend to be kind of an orangey yellow color. However, I think if you think much like sodium street lamps, I think the problem there is probably the image that I had there probably didn't capture the color quite, I suppose, as well as it might have, because if you think of the old sodium street lamps, once they first turn on, they tend to be kind of an orangey color, and then they go yellow after a while. It's the same with laser guide stars. Once they're first shot, they're quite an orange color, and then they tend to go a more yellow color, which is probably why it looks maybe a kind of a yellowy green color. So to the best of my knowledge, all laser guide stars tend to be sodium laser guide stars in order to interact with that layer of sodium atoms in the atmosphere. I don't know if there'd be any benefit of using another element for that laser at the moment in time anyway.
Great. Thanks very much.
Okay. Joe,